Welcome back. In the last session, we had seen DC circuit, AC circuit, and we combined both, and then we got self-bias circuit from DC analysis, and then common emitter amplifier from AC analysis. Then we combined, and then we got this circuit, and then I told this is what is our final BJT amplifier, which has both DC as well as AC, right? Then last session I didn't give sufficient time to draw all these circuits. Now maybe you can write down. Therefore I'll explain a little bit about the combined circuit. Okay, we know individually what is DC circuit and then what is it doing, and we know individual AC circuit what is it doing. Then let me explain a little bit about the combined circuit and then I'll name the circuit. Okay, just try to write in 2 minutes. If you ask me what is the name of the circuit, this is what people call it as RC coupled CE amplifier. This is what is RC coupled CE amplifier. We are coupling through capacitor. Here also coupled. Here also coupled. Therefore, we are coupling through capacitor, RC coupled CE amplifier. But we have something called direct coupled amplifiers, right? But this is not direct coupled amplifier, where we are not giving VI directly to your amplifier, right? We are giving VI with respect to capacitor CB. Then this is what is coupling the AC signal on top of the DC signal, which is what is set by VCC R1 R2. That's why this is RC coupled, not direct coupled. But ultimately we want direct coupling amplifier. Because of RC coupling there is a limitation. That part I will explain. Okay, that's fine. Over, right? Now assume that this is only given in the examination. If this is only given in the examination, how will you get DC circuit? I told you a procedure. If you start, go to the starting of the classes, any circuit which is what is given, then based on the problem statement, classify the problem into either AC analysis problem or DC analysis problem. Once you know the problem is related to AC analysis problem, then immediately get AC circuit. If you know the problem is related to DC analysis problem, immediately get DC circuit. Okay, that is what I told. Now let us say you want the DC circuit from this. Okay, in the problem statement asking for the output DC current, collector current IC. Then how will you calculate? This is what your combined circuit. We know that for DC, capacitor acts as a open circuit. This capacitor acts as a open circuit. This capacitor acts as a open circuit. You take out all these things, then it is left with what? Self-bias circuit. That is what is your DC circuit, right? Now coming to AC analysis, how will you get AC analysis? I told you, right, for AC, capacitor acts as a short circuit. This is what is acting as a short circuit. We are assuming that it is short because at Other than low frequency signal, right? The signal frequency, the signals whatever you want to amplify, those signal frequencies, assuming that the capacitors will be shorted. Then how will you choose the capacitor values? If you know the signal frequency range at the input, for the minimum signal frequency, at least the capacitor whatever you are having here, this capacitor in parallel to, in combination to the input impedance, and this impedance which is reactance basically Z1, Z2, the Z2 divided by Z1 plus Z2 into Vi should be equal to Vi approximately. For what capacitance value for the low frequency signal at the input, this is almost short circuit, or the enter voltage will be coming to your amplifier input. That is what is the value of C we have to choose. Okay, that is easy only. Therefore, if you know the signal frequency range, let us say 20 Hz. For 20 Hz, even I want this to be almost short circuit. Then for 20 Hz, choose the CB value. Then you will get some reactance. Find input impedance. Then input impedance in parallel to this. Therefore, your input impedance should be very much greater than this value, or this reactance should be very much less than input impedance value. Then the enter voltage will be coming to your input of your transistor. Therefore, we have to choose the value of CB such that the combination of Z1, Z2 along with the signal frequency will be almost shorted. Therefore, if CB is almost equal to shorted, then you will get Vi is equal to, the Vi will be applied to your transistor input. Okay, that is fine. Then how will you get AC circuit from this? How will you get AC circuit from this? Therefore, how will you get AC circuit? What is AC circuit? This is what is the circuit which is given in the examination. If this is what is given in the examination, how will you get AC circuit? Just listen. This is important. Therefore, from this AC circuit, you may say that this is what is AC circuit, right? Actually, this is what we need from AC circuit. Are we getting the same circuit from this circuit or not? That is what I am explaining. I think DC circuit is straightforward. Why? From this, how will you get DC circuit? Capacitor, open, open, open. This is simply left with self-bias circuit configuration. That is what is matching to the required circuit. Similarly, for AC circuit also, after getting AC circuit, if that is matching to common emitter amplifier, yes. That is what I am trying to explain from this, how to get AC circuit. Wherever for AC analysis, short, 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 and VCC is also connected to ground. Wherever you have DC quantity, that should be connected to ground. We have to replace with the dynamic resistance. Okay, then tell me, this is what is the transistor. Now your emitter is connected to what? Shorted, because this is short circuit. Therefore emitter is connected to ground for AC analysis. Emitter is connected to ground for AC analysis. Then what about collector? This is connected to ground. Therefore this is connected to ground, and this is short circuit. Can I say this RC is coming in parallel to, because this is also connected to ground. This RC is coming and this is short circuit. This RC is coming in parallel to RL. Therefore RC parallel to RL from collector to ground. That is what we have. RC parallel to RL. That is what we have. And this is what is our output voltage V0, right? Then what about input side? This is shorted, and whatever voltage you have, this VCC is connected to ground. When this VCC is connected to ground, this R1 is coming in parallel to, because this is connected to ground, this R1 is coming in parallel to your R2. That combination is coming in parallel to your Vi, because this is short circuit for AC signals. Therefore that is the combination that you will get basically, because this is AC ground, R1 in parallel to R2, and this is what is our input signal Vi. Okay, now this is what is collector, emitter, and then base. But I want to explain one more point. Now tell me if there is a example, there is a battery in parallel to a resistor. This is 10 volt battery but having some value of R. A voltage source in parallel to a resistor. Equivalently people represent, because the voltage will not change in parallel, equivalently people represent this as voltage, because the terminal voltage whatever we are having, that is nothing but 10. Therefore this is what is 10, it won't change. Similarly, if you take a current source and in series to current source there is a resistor. Let us say this is 10 ampere, and we know that in series doesn't mean that it is not open, some load is connected. Okay, then but we are interested for this part, this portion. Now, in series, current is constant, right? Then whether you have R or not having R, the current what you are pumping to the load are open terminals, not open terminals. The terminals what you are interested for, that current is about 10 ampere. Therefore, in series, whatever current you have, that is equivalently, even though you represent R or you don't represent, doesn't matter. Because the amount of current which is what you are pumping through these two terminals will be 10 ampere, even though you have R or you don't have R. Therefore, now tell me, this is what your input signal in parallel to a resistor, that is what you are applying. Remember, in parallel voltage is constant, whether R1, R2, whether it is present or not, the amount of voltage what you are applying to your transistor is nothing but Vi only. That is what is the signal which you want to amplify. Therefore, you can say this is nothing but, therefore, now the final AC circuit is nothing but, effectively this is simply Vi. You can ignore R1, R2 combination which is not impacting the AC signal what you are trying to give it to your transistor. Then this is what is your load. I can say this is what is RL dash, where RL dash is nothing but RC in parallel to, this is what is called effective load. Therefore, and this is what is your V0, collector, emitter, base. Your RC coupled CE amplifier, became simply common emitter amplifier for AC analysis. Therefore, that is what is matching to this. But here the load is nothing but what? Effective load, which is RC in parallel to RL. Actually, this RC is DC bias resistor. This is what is the effective load, which is what is our loudspeaker, right? But in the case of AC analysis, whatever resistor which is present here, that is what we took as a load. Yes, I agree. But what is the effective load for the RC coupled C amplifier? That is RC in parallel to RL. That is what is the load for your common emitter amplifier. That is what we need to consider, and we need to solve the problem. Therefore, now this is what is our C amplifier. Everybody understood? Yes. We did them separately. Now even after combination also, for AC analysis we are getting common emitter configuration. For DC analysis we are getting self bias circuit. Therefore, fine. Even though we are coupling through capacitors, we are getting self bias circuit from DC analysis and common emitter amplifier from AC analysis. You can write this decomposition. Maybe one more session to complete the theory part of or the concept on BJT amplifiers. Then from next session onwards, after completing BJT amplifier, we need to solve the problems related to chapter 2 or related to BJT amplifiers. It will take 3 to 4 sessions to cover the problems, the workbook problems related to chapter 2. Workbook as well as the test what you are going to write. Okay. Just a minute, try to write in the meantime. Hope this is over. Now, I think this is the time to explain why we are using cell bias circuit in DC analysis. Why not collector to base bias, right? Maybe this is the reason. Let's do DC plus AC analysis, okay? Now, AC circuit we need common emitter amplifier, but what is DC circuit? The DC circuit is nothing but collector to base bias circuit, right? This is collector, base, emitter, and this is what is VCE, IC. Those things we already represented from DC circuit or DC analysis. Okay. Now, how to combine? Let's combine, right? Now, we want DC plus AC. Therefore, DC. Don't write. Just observe here. Then you'll get the answer. Therefore, first of all, we need to start with the DC circuit. Okay, now this is what is our RB. Now, the operating point is set VCE, IB, IC. I want to apply AC signal on top of the DC voltage. Therefore, the DC voltage what you have, the VBE is set by VCC, RC, RB, right? Fine. But I want to couple AC signal. I told you, right? If you want to couple any AC signal on top of existing DC voltage set by the local circuitry, we need to have input coupling capacitor. Therefore, this is what is your input coupling capacitor, and let us say this is what is your input voltage VI. I am representing like VI. Actually, VS and then RS. That is what your practical voltage source. Assuming that there is a Darlington pair, there is a CC amplifier which is what is doing the job of coupling, job of buffer action. That I am not showing, but this is what is the signal. Whatever signal you are applying here, that is what you are trying to couple to the DC circuit, which is collector to base bias. Similarly, whatever DC voltage you get and whatever AC voltage you are getting on top of DC voltage, we want to take out the DC voltage and apply only AC signal to the load. Let us say this is your loudspeaker. This is RL and this is what your V0 and this is what your CC. Fine. But tell me, this is what your feedback resistor and this is what is acting as negative feedback resistor for DC analysis, and that is what is stabilizing your Q point. But remember, if you keep it like this, the same RB is also acting as negative feedback for your AC signals, then RB does not know whether the output collector current is changing because of the temperature or collector current is changing because of the input AC signal. Then it will try to attenuate the change in IC because we want to stabilize IC, we want to stabilize operating point, but the IC change due to input signal also will be controlled by your RB, which is nothing but negative feedback. Then your AC gain will be decreasing. Actually, this we did not see in the case of AC analysis, but we have seen CE with RE amplifier in AC analysis. But remember, if you have like this and then if you do AC analysis, your gain will decrease. but that part I'll explain for feedback amplifiers how to get the gain formula. But now qualitatively I can say that this is what is going to reduce the AC gain. But I don't want RB for AC analysis, I want this RB for DC analysis. What to do? In the case of RC coupled C amplifier, we added just simply a capacitor in parallel to RE. Therefore, it is bypassing. Therefore, we don't want RE for AC analysis. It is bypassed. But we want RE for DC analysis to have Q point stability. Therefore, we kept it. Therefore, capacitor will act as an open circuit. Then RE will be present. Similarly, here I want this RB for DC analysis. I don't want this RB for AC analysis. What to do? Tell me. What to do? Shall I put capacitor in parallel to it? Like your bypass capacitor, right? Okay, if I keep it like this. Now, tell me, for a DC, capacitor acts as an open circuit, open, therefore RB is there, this is also open, this is also open, this is simply connected to base bias circuit. Fantastic, satisfying the operation or the requirement of the connected to base bias circuit from DC analysis, fine. But let's say for AC signal. For AC signals, what is this? Short circuit, right? Your input, short circuit, short circuit, short circuit. Then tell me what your output. Your output is now same as input. Then your gain is equal to 1. Right? Therefore, whatever capacitor you added in parallel to it, it is serving the purpose of having RB during AC and DC analysis, but it is shorting RB during AC analysis, which we don't want. What do we need? First of all, we don't want RB at all, means it is equivalent to infinity we want. Then what to do? Shall we put capacitor in series? If I put capacitor in series, let's see. For a DC, capacitor acts as an open circuit. Then RB is not there between collector to base. Actually, we want RB. For AC, short circuit, which is providing RB in between collector to base. Actually, we don't want RB. Therefore, we are getting exactly opposite what we need. Then, tell me, I want reciprocal element of capacitor, then whatever we had seen now, exactly opposite to that we will get it, which we want. What is reciprocal of capacitor? What is reciprocal of capacitor? Reciprocal of capacitor is nothing but inductor. Therefore, if you add inductor, it will serve the purpose. Now let's see. For a DC, inductor acts as a short circuit. Then RB, feedback resistance, is provided between collector to base. That is what we want. For AC, inductor acts as an open circuit. Then open. Then RB is not connected, then it is simply common emitter amplifier, right? Therefore, we need to have inductor. Therefore, now tell me, this is what is exactly same as RC coupled CE amplifier. But in the case of RC coupled CE amplifier, we don't have inductor. But here, if you want to get DC plus AC action together from one circuit, we want this type of structure where we need inductor in the feedback, then only it will solve the purpose. It will serve the purpose what we need. But remember, inductor is bulky in the nature. We don't want to use inductor. Especially in the case of integrated circuits, it occupies more area. If it is occupying more area, remember, then if you have already alternative solution using capacitor, which is nothing but RC coupled CE amplifier, why do you want to use this? Nobody uses this circuit. Because we have already alternative solution which is nothing but RC coupled CE amplifier, right? That is the reason why nobody uses. That is because of only inductor. I think now this is what is explained why we are not going for collector to base bias circuit and why are we going for self bias circuit, because self bias circuit is only dealing with capacitor, but here it is dealing with inductor. Okay, take it. But remember, whatever AC gain you are getting from this, the same gain you are getting from RC coupled CE amplifier. Everything is same, but because of inductor, we don't want to use it. That's it. Take it. That's why we will not see the circuit at all, because nobody uses. If nobody uses, no popularity, then that won't be visible in any textbook. With this I can say DC plus AC analysis, and finally we got an amplifier. Tell me, what is our BJT amplifier now? RC coupled CE amplifier. That is what people use. Therefore, I think from past 20 to 22 sessions, right? We are always looking for BJT amplifiers, different configurations from DC AC analysis and different bias and circuit from DC analysis. We got what is the final amplifier from AC analysis, which is CE amplifier, and we got final circuit from DC analysis, which is cell bias circuit. We combined both of them, we got RC coupled CE amplifier. Therefore, now out of so much analysis, we got to know the final amplifier. That is what is RC coupled CE amplifier. It is not straightforward, right? We studied so many circuits from AC analysis and different circuits in DC analysis. Then finally we got RC coupled CE amplifier, which is what is giving you Q point stability and keeping the transistor in active region, which is nothing but biasing, and finally common emitter configuration, which is going to give you more power gain. Okay. Therefore, ultimate amplifier is nothing but RC coupled CE amplifier. Now for that RC coupled CE amplifier, we need to do frequency response analysis. Because now the frequency is coming to picture, the H parameter model, whatever we calculated, that is true only for low frequency signals, or I can say mid range of signals. At very high frequency, that H parameter model failed because it did not consider or it did not model the BJT internal capacitances. For that we have to take hybrid pi model, which we had seen before. Then using that model, we have to find the transfer function of RC coupled CE amplifier, and we need to calculate bandwidth, which is not required to solve. Right, then directly we can go for qualitative analysis of RC coupled CE amplifier, like frequency response analysis. Then what is bandwidth? Then if you take multi-stage configurations, then what will be the overall bandwidth? That is what we will see. With that I can say BJT amplifiers are over. Then we can go for workbook problems or the previous GATE problems. Then we can switch to chapter 3, I can say FET amplifiers. But FET amplifiers will not take the same time as BJT amplifier. You will understand why it won't take that much time. Just wait and see. Okay. Over? Okay. Now write down the last topic under BJT amplifiers. Okay. Now frequency response analysis. Of RC coupled CE amplifier. This is what is our ultimate amplifier, which we are seeing. Right? Therefore, now Therefore, this is what is our RC coupled C amplifier. Now, we want to know what is frequency response analysis, right? When you ask me frequency response analysis, frequency response analysis, basically this is nothing but Bode plot. I want to draw Bode plot, but only magnitude response. Therefore, it is associated with magnitude response, and phase response. Okay. Therefore, what do you mean by frequency response analysis? Then, with respect to input signal frequency, right? With respect to input signal frequency, what is the gain of the amplifier? What is gain? Output peak to peak divided by input peak to peak. That is what is our gain. What is the gain of the amplifier with respect to input signal frequency? That is nothing but your magnitude response. What is phase response? What is the meaning of phase response? The meaning of phase response is with respect to input signal frequency, what is the delay between input to output? The time domain delay is converted into the phase response with respect to frequency. Therefore, ultimately both are related to time domain only, but we are looking for frequency response analysis, which is faster to analyze. That is the reason why people take into frequency response analysis, but I am going to plot only magnitude response, okay, not phase response. I am looking for only magnitude response to define bandwidth, okay. First of all, take the circuit and then what is frequency response analysis. Before applying or before getting magnitude response of your RC coupled C amplifier for a practical circuit or system, what should be magnitude response, what should be phase response, let me explain, then we'll go to the frequency response of your RC coupled C amplifier. Qualitatively I'll explain. Quantitatively we need to replace the BJT with hybrid pi model, then we need to get it, right? That part I'll explain. First of all draw, then maybe within 15 minutes I'll try to complete the expectation of magnitude response and expectation of frequency response with respect to frequency for any system, then whether our RC coupled C amplifier is following in that expected region or not. Okay, let's see. Over? Okay. Now don't write, this is what is important theory not only for your RC coupled C amplifier. If you take your signals and systems or control systems, what is the expected magnitude response and the phase response, right, for any system. Now don't bother about all those things. Now just a theory, right? I'm just considering a system, any system. We don't know what is there inside, but it is defined with what? It is defined with output signal y of t and input signal x of t, right? Therefore defined with input signal x of t and defined with output signal y of t. What do you want? Actually, whatever signal you have, it could be sine wave or it could be anything. It could be voice signal, it could be audio signal, right? It could be video signal. Whatever may be the signal which you are giving to your system, I am expecting constant gain for any frequency for any signal frequency what you are giving at the input. Whatever may be the input signal frequency, I am expecting same gain. Right? Then what I am expecting the gain of A. I am expecting the gain of A for any signal x of t. Right? No need to specifically speak about the frequency. It is simply x of t. Any signal in time domain should have the gain of A. Therefore, y of t should be equal to A into x of t. Then every system will have some delay. Obviously, every system will have some delay, time domain delay. Then whatever signal you are giving here, after multiplying with A, definitely this signal A into x of t will have at the output after some time. Therefore, let us say this is what is having delay. Let me say it is having delay of TD. It is having some delay of TD. Then what are we expecting? Y of t should be equal to, for any signal, the gain should be A, and the input signal can have some delay. Let us say T minus TD. Right? Therefore, this is what we are expecting. Right? Now, therefore, this is what is representing the delay of the system, time domain delay. Now, this is what is time domain information, where x of t can be any signal. For any signal at the input, y of t is expected to be equal to A, which is constant for any signal what you are applying, and with a delay of TD, the delay should be either 0, ideally it is 0, but practically it is defined with some delay. That is what is TD. Let us say that is what is TD. Now let me convert into frequency response. That is what is easy. Right? What is x of, if x of t, then you will get x of s. Finally, I will substitute s is equal to j omega. That is fine. Then y of t, this is what is having y of s. Therefore, tell me what is y of s. If x of t is x of s, then a into x of t, a into x of s. If x of t is x of s, then what is x of t minus td? That is nothing but a into x of s into e to the power of minus s into td. This is what is your y of s. Then tell me what is your transfer function. Therefore, transfer function h of s is equal to y of s divided by x of s. Therefore, what is this? Y of s is nothing but a into, therefore after doing x of s will be cancelled, and this is e to the power of minus s into td. Then what is h of j omega? If you take h of j omega, which is nothing but a into e to the power of minus j into omega into td. Now if you write from this, what is mod h of j omega? What is mod h of j omega? The magnitude is nothing but e to the power of j theta, which is cos theta plus j sin theta. Then what is root over cos theta plus j sin theta? Sorry, what is magnitude of cos theta plus j sin theta? Root over cos square theta plus sin square theta. That is 1. Then it is left with what? A. Then what about phase angle? Angle of h of j omega, e to the power of j theta. Theta is nothing but minus omega td. This is what is our phase angle with respect to frequency, and then this is what is the gain with respect to input signal frequency. Therefore, the time domain signal, the time domain processing, or the time domain relation converted into frequency domain, magnitude response, and then phase response. Therefore, if I plot the magnitude response and the phase response, let us say this is what is omega, and this is what is mod h of j omega. If you want, you can convert into dB also. 20 log of this will be, which is nothing but dB, gain in dB. Then tell me what are we expecting? Whatever may be the signal, I am expecting gain A, which is nothing but whatever may be the signal frequency you have. Whether the signal frequency is having 0 to infinity, I am expecting the constant gain A. This is what is expected gain. My gain should be constant irrespective of your input signal frequency. The input signal frequency can be anything, but it should have all the input signal frequencies, all the signal frequencies should have the gain of A. That is what is saying that distortionless system, or I can say this is what is having gain of A. Now, for example, angle of h of j omega is equal to minus omega td. Then, what is the meaning of it? This is what is omega. Then, this is what is angle of h of j omega. Then, what is it supposed to be? If you want to have fixed time, or fixed delay in time domain, we should have linear phase response. What do you mean by linear phase response? Y is equal to mx, where mx is nothing but minus td is the nothing but slope into x. Y is equal to mx, where slope is nothing but minus td. Negative slope is nothing but positive time domain delay. Positive slope in frequency response is nothing but negative delay. Negative delay is nothing but anti-causal system or anticipatory system. Before giving your input, your output will be responded to the input even though you are not applying. That is not practically true, right? Practically that is not true. Practically every system will have either zero delay or positive delay. Then positive delay means negative slope. That's why you will have the slope something like this. The system which is having linear phase response, that is what is having fixed time delay in time domain. The system which is having constant gain, then that is what is having constant gain for any signal what you apply at the x of t. Therefore, ideally, I am expecting the gain of the system to be constant and the phase of the system should be linear. The system which is having these two, that is what is said to be saying that it's satisfied or it doesn't have any frequency distortion and doesn't have any phase distortion. If the system is not having linear phase response, then people say that the system is having phase distortion. The system which is not having constant gain and then changing with respect to frequency, wherever the gain is changing with respect to frequency, people say that it has frequency distortion. Okay, that's fine. You take it. This is what is the expectation value. Then we are going to plot the magnitude response of your RC coupled CE amplifier, and then we are going to look for where in what frequency range the gain is flat. There only we will try to operate. That is nothing but basically bandwidth. The range of frequencies in which your gain is almost constant, that is what people call it as bandwidth. We have two types of bandwidth. One is absolute bandwidth and 3 dB bandwidth. That part I will define. First of all, you take the theoretical definition. Maybe I can say I can stop the session now. In the next session, we will see the manual response of RC coupled CE amplifier. Okay, we are expecting it to be constant, but definitely we will not get constant gain for all the frequencies because of some reasons. Those reasons all I want to explain. Therefore, let's see those reasons and then let's see the frequency response of or manual response of RC coupled CE amplifier. Take it. Normally people take, if you take any control systems or signals and systems, right, people take reference of 1, gain 1. With respect to 1 only people define. Similarly, the reference of phase shift minus 180 degrees and all people start. That is what is the reference. What is the reason? That part I will explain. I will try to explain from oscillator principles. Always remember y-axis 1 is the reference. In dB 0 dB because 20 log 1 is 0, and for frequency response 180 degrees, minus 180 degrees or 180 degrees, that is what is the reference. 1 and 180 degrees, these two are references with respect to y-axis. But normally typically 0 0, right? But 0 0 they are not reference for us. Why they are reference, like 1 and then 180 degrees, that part I will explain from oscillator principles. Okay? Yeah. Therefore, I can say there is no frequency distortion. No frequency distortion. If gain is flat, then there is no frequency distortion. If phase response is linear, then there is no phase distortion. If phase response is constant, we don't want constant phase response, remember. We want linear phase response, therefore there is no phase distortion. Actually there is one more distortion called amplitude distortion. That part I will explain. Therefore, but let's see, this is what is a system which is not having any gain variation with respect to frequency, that is called no frequency distortion. The system which is having linear phase response, that is said to be not having phase distortion. Okay? If this is over, I will stop now. Then we will see the frequency response or magnitude response of RC coupled C amplifier. Okay? Thank you.